Welcome everyone. In this video, I am going to discuss about Riemann sphere and stereographic projection. I hope you are familiar with complex plane. Actually, it is a two-dimensional plane which represents complex numbers, right? So Riemann sphere is the extension of the complex plane. That is, we are coming across the term extended complex plane. In the extended complex plane, we are adding one point to our complex plane. This is called as one point compactification of the complex plane, or we can denote that as extended complex plane. Right. So I will mention what I just said. Extended complex plane is denoted by C hat or C infinity. Normally I am using C hat notation, therefore I'll go with that. So C hat is equal to C union infinity. That means I have my complex plane and I'm going to add another one point, that is infinity. So this is equal to my extended complex plane. Right. Now the nice thing is there is a nice relationship between this extended complex plane and unit sphere. That means there is one-to-one correspondence between our extended complex plane and unit sphere. Or in other words, we can identify extended complex plane as a point which lies in the unit sphere. This is very interesting. Therefore, when we are dealing with sets in our complex plane, we can think them as sets in unit sphere. In the complex analysis, in many places we are using this fact, especially when we are dealing with neighborhood at infinity, then we cannot visualize them in complex plane. Then we need to shift to Riemann sphere, and we need to think in terms of Riemann sphere. So that's the story. So then we will construct algebraically how points in Riemann sphere and points in complex plane related to each other. So according to my figure, I have north pole of my unit sphere and then I have a point simple z which lies on my complex plane, and I have drawn a line which connects my north pole and complex number z. Right. So while I was drawing this line, it hits the sphere at capital Z. So you can choose any point in the complex plane, and you need to do is draw a line which passes through north pole and the complex number. Then at one point of the sphere, that line hits the sphere. So that is the corresponding point in the sphere to this simple z. So I will explain that again. I have my point simple z here, and the corresponding point to that complex number is capital Z. So capital Z is the corresponding point in the sphere of simple z. Right. Now we'll derive the expressions algebraically. So I think the first thing that you need to have is have a good intuition about what is going to be happen. So the thing is, we are drawing a line which connects north pole and our complex number, and it hits while it was drawn, right? So we need to find the coordinates of that point capital Z, right? So that is the story, and I will derive expressions algebraically now. Right. First thing that we need to do is I have to find the equation of a straight line which connects my north pole and complex number z. So I will denote that line as simple L. So L will be, I think you are familiar with how to find the equations of straight lines in three-dimensional spaces. So Tn plus 1 minus T into simple Z denotes the equation of line which passes through N and Z. If you put t equals 1, then you are at the north pole, and if you put t equals 0, then you are at the point simple Z, right? So in other words, L is equal to t0 0 1 plus 1 minus t in x y 0, and if I simplify this, I'll have x1 minus t plus comma y1 minus t comma t. Right, so this is the equation of my line, and then I know that my point capital Z is lying on this line. Capital Z is lying on simple L. Therefore, I can write capital Z as x1 minus capital T, because simple T is my general parameter, and I can have capital Z at some specific parameter value. I will take that parameter value as capital T. Right. And also I know another fact about capital Z, that is capital Z is lying on this sphere. Therefore it satisfies the equation of a sphere. Right. Then I am going to use that fact. Since capital Z is lying on the unit sphere, it satisfies the equation of unit sphere. Therefore I can have x square 1 minus t square plus y square 1 minus t square plus t square is equal to 1. Right. Then from these two terms I can have 1 minus t square out, then I'll get x square plus y square plus t square equals 1, and I know that xy is my complex number z. Therefore I know that the magnitude of complex number is denoted by x square plus y square square root. Therefore I can have modulus of z square here. Right. Then I need to find capital T, because I need to find the corresponding point of simple Z in the unit sphere. Therefore I'll write this as a quadratic equation of capital T. Then I'll get t square out, then I can have z square plus 1 and minus t plus t minus 2. I'll go with my usual notation, this notation for simple Z. right? So if you simplify this equation and if you find the values of t, you can have two values for capital T. I'm not going to do the simplification. You can have two answers, that is t equals 1 and t equals z square minus 1 over 1 plus z square. You can solve this quadratic equation and have this answer, and t cannot be equals to 1 because capital T equals 1 when your point is at when capital T equals 1, your point should be north pole. But in this case, my complex number is in the complex plane. Therefore, its corresponding point in the unit sphere cannot be north pole. Therefore, T cannot be equal to 1. Therefore, T equal to T is mod z square minus 1 over 1 plus modulus of z square. You can simplify and get this answer and check my answer is right or not. Then after you find capital T, you are done, because if you know the capital T, then you can write your point capital Z, that is x1, x2, x3, and that is equal to, what is my x1? X1 will be, I'm not going to simplify, my x1 will be these three, x1, x2 and x3 are these three values. In this one, x1, x2 and x3, right? The next one will be x into 1 minus modulus of z square minus 1 over modulus of z square plus 1. Like that, you can have expressions for x1, x2 and x3. I'm not going to do the whole simplification. You can easily do that, right? Now we found that there is a nice correspondence between unit sphere and complex plane. So the next problem is, what is infinity? So that would be the nice problem, because if you consider the real line, then you can go to infinity in two directions. One is positive direction and one is negative direction. But in the complex plane, there is only one infinity. So what is that infinity? Because if you take any point which lies in the complex plane, then the line that you draw, that means you are going to connect through the line which passes through north pole and that point, then it hits somewhere in the unit sphere, and that is not the north pole, right? So if your point is lying in the complex plane, then the corresponding point in the unit sphere will not be north pole, right? So then what will happen if you go far and far away? That means if you this is your x, y and z axis, and this is your unit sphere. And what will happen if your points lie very far? Let's say z is somewhere here, then you are intersecting the unit sphere at a point that is very closer to north pole. So infinity means the that means the by thinking in that way, you can happen you can have an idea about what will happen at z equals infinity. That means when you go far and far away in the complex plane, then you are getting closer and closer to North Pole, and at infinity you are at the North Pole. So that is the interesting fact here, right? So I will mention that part. At z equals infinity, the corresponding point in the unit sphere will be the North Pole, right? So you can visualize anything that is happening in the extended complex plane in the unit sphere, because it has infinity and it is equal to North Pole, and any complex number which lies in the complex plane, there is a corresponding point in the unit sphere, right? Unique corresponding point, because if you take 2 points z1 and z2, there are two distinct corresponding points in the unit sphere, right? And also if you take one complex number in your complex plane, there cannot be two points which corresponds to that complex number in your unit sphere. There is only one corresponding point to one complex number, right? So actually this relationship is bijection, but there's not a map. We cannot have a function how this map maps complex numbers to unit sphere, but there is a one-to-one and on-to correspondence between your complex plane and unit sphere, right? That means at each point, that means if you take any point in this sphere, there is a corresponding point in the complex plane, and to each point in the complex plane there is a unique point in the sphere. It can be found by using the algebraic expressions that we derived. I hope you had some idea about Riemann sphere, and in the next video we will discuss about how differentiability behaves in complex plane. Okay, thank you for watching.